Welcome to the New Books Network.
Hi everyone, and welcome back to New Books Network. I'm Galina Limorenko, doctoral candidate in neuroscience with a focus on biochemistry and molecular biology of neurodegenerative diseases at EPFL in Switzerland, and will be your host today. Today we'll be talking to Aubrey Clayton about the new book, Bernoulli's Fallacy, Statistical, Illogic, and the Crisis of Modern Science. Aubrey Clayton traces the history of how statistics went astray, beginning with the groundbreaking work of 17th-century mathematician Jacob Bernoulli, and winding through gambling, astronomy, and genetics. Ranging through across math, philosophy, and culture, Bernoulli's fallacy explains why something has gone wrong with how we use data and how to fix it. Aubrey, welcome to the show.
Thank you. Thank you for having me.
So as we're going through the unprecedented times of the recent global pandemic, I was wondering if you could start by reflecting on how has this affected you and your work, and maybe some main takeaways that you have gathered from this experience.
Well, it's obviously a difficult time for everyone, and a difficult time as an author, particularly a first-time author. I haven't had a chance to connect with people in person the way that I would have liked. Fortunately, I've been able to talk to a lot of people virtually, but I would have preferred doing some readings and seeing people in person. I think as far as my process is concerned, the main difference during the pandemic has been just having easy access to resources online. Really has made some things easier for me, being able to go to various library resources all around the world, just from the comfort of my office. I think the other way in which the pandemic has affected things is that statistics is very much part of current events now. And a lot of the writing that I've been doing over the last 2 years has been about COVID statistics and the uses of statistics in making sense of the pandemic and of risk more generally. So that has provided, unfortunately, a lot of opportunities of things to write about. But I think it's been a useful reminder that statistics continues to be relevant and vibrant and an important part of the way people make sense of the world, especially in times of crisis like this one.
You must have become a go-to person about statistics about COVID for your friends and family.
I have a bit, and I think that's probably the case for anyone with a statistics background. I think all of a sudden, I think we've had to give our friends and family a crash course in kind of statistical thinking and probabilistic reasoning, especially when it comes to test accuracy rates and incidence rates and things like that. So I hate that the circumstances have led us to this, but I do appreciate the value that I'm able to give to those people under such circumstances.
So can you tell us a bit more about yourself?
Sure. So my background is in mathematics primarily. So I grew up in a very mathy family. Both my parents are now retired math teachers in high school. I went to university to study math and statistics also. And when I was there, I got exposed for the first time to kind of mathematical probability, which was to become my area of focus. One of the kind of very important moments that happened to me when I was a student was when I was in a statistics course in my sophomore year, and we studied the Monty Hall problem. We learned about this famous example of a probability paradox that a lot of people struggle with. And part of the story of that problem is that it was when it was originally kind of popularized and the columnist Marilyn Vos Savant published her solution to the problem, she got a lot of angry mail from people with backgrounds in math and statistics, and all these PhDs and professors writing to her, telling her she's made an obvious mistake and how dare she, and what an embarrassment, et cetera, et cetera. And she was right. I remember thinking about whether I wanted to continue in math and statistics studies, and feeling like I had an obligation to do better than these people that I was reading about, and maybe to inject a little humility and a little patience into the world of math and stat research, and maybe use examples like this very tricky problem as a kind of teachable moment, and how even people with advanced training can get mixed up and can get very upset and confused. So I think that was an important kind of turning point for me. It was when I sort of decided that I wanted to continue. So I did carry on. I went to graduate school to study math and in particular probability theory. And I think the other kind of turning point for me was during my time as a graduate student. I got very deeply immersed into the kind of mathematical theory of probability, but without ever really having to confront the question of what probability means in the real world. And I had an opportunity to work on a problem with a friend of mine who came up with what he thought was a strategy to make money gambling on professional basketball. And he provided me this data and asked me basically, is there something to this theory? Can you show that this is statistically correct? And I realized that I didn't really have any clue what I was supposed to do with all that data, even though I had a kind of background in statistics and probability. So I think just the course of and that moment of having to decide what to do in a real problem when there was money on the line, there was potentially money to be made, and not really having the first idea of what to do with it, I think it led me into really examining the philosophy of probability and statistics, and I think I was ultimately confronted with this question of what is probability. And it was a very destabilizing question to have to ask midway through my graduate career, having studied mathematical probability for many years at that point. But I realized that I never really studied the philosophy of probability. So that was what led me to the work of E.T. Jaynes, a sort of American physicist and probability philosopher. And he wrote a very influential book called Probability Theory: The Logic of Science. That when I found that book, it sort of changed my life. And I decided from then on that I was going to dedicate myself to spreading his ideas and distilling them and making them accessible to as wide an audience as I possibly could. So that's essentially where we are today.
And along your career journey, were there any colleagues or mentors that really supported you along the way?
Well, I was lucky to have a lot of colleagues and mentors. I think the department where I studied at the University of California, Berkeley, is an amazing institution, and I learned an incredible amount from my fellow students there, as well as my advisor, Steve Evans, who is he's both in the mathematics department and the statistics department, a very kind of unusual interdisciplinary figure. But really what I kind of came to realize in the course of doing this investigation is that there is not really an institutional support for this kind of thinking, that you can study mathematical probability for years and years without ever really having to confront the question of what probability is. And so apart from this book of E.T. Jaynes, I didn't have a lot of access to that way of thinking. I think nowadays things are somewhat better because people connect online, and part of what I've tried to accomplish is providing that resource and that guidance for people who are struggling with the same questions I was struggling with. But I did feel a little bit like I was on my own at that time.
It sounds that you had a very exploratory approach in your career, really finding things out, didn't you?
Yeah, that's fair to say. I think I was maybe somewhat typical grad student in that I was drifting for quite a while, trying to decide what I wanted to study, having many kind of false starts and failed attempts to make progress in various problems. And I was lucky that I had the freedom and the flexibility to continue exploring and to find resources like books online or at the libraries. So yes, I was definitely an explorer, and in a lot of cases, I was just sort of following my nose and seeing where my instincts took me. But I think if I could go back and really identify the ways of thinking and the kind of habits of thinking that really helped me in that period of time, and if I could make an advertisement for people to study pure math, it would be this: that I think learning to think slowly was a very important part of my exploration at that time, and really learning to examine all of the assumptions that go into an argument and asking for precise definitions of all of the terms that are being used, and really just slowing down the thought process so that you go methodically one step at a time. I think that's a habit of thought that comes from mathematical training that I think is especially important in realms like statistics and probability, where it's very easy to let your intuition kind of run ahead of your analysis and to lead you into some traps and some paradoxes and turn you around. So I think what's needed in that field really is some slower thinkers. And I think that that's something that mathematicians really do have to offer.
So your book is Bernoulli's Fallacy, Statistical, Illogic, and the Crisis of Modern Science. So can you tell us, how did you come to writing it?
Yes, so I was led to writing the book by a desire to really share some of these ideas of E.T. Jaynes with a wider audience. And in particular, going back a few years now to around 2018, I had the experience of really thinking about these topics day and night, and having a strong desire, almost like a physical weight that I felt I was carrying around with me, that I needed to set down to share these core ideas with people. And around that time, there was also a lot of news about the replication crisis in science, and the fact that science was having difficulty with established results seemingly not being replicable. And I think that was what prompted me to really write the book the way that I did. I had this thought that I could connect these stories together, and I could sort of answer the question of what would this way of thinking have to say about the replication crisis, and how might this be relevant to the very active and ongoing debates that people are having about statistical methods in the sciences. And maybe, this could be an opportunity for people to take a step back and rethink the way that statistics is used.
So let's delve into some of the topics that you cover in your book, and we can start with the easiest question, I suppose. So what is probability?
Yeah, so the easiest and the most difficult question. So maybe to go back one step, I think when I talk about the problems of statistics, what I argue in the book is that there is really a fundamental misunderstanding about the nature of probability, and that is what has led statistics to have the problems that it does. So answering the question, what is probability, at the end of the day, I think is the precursor to all of the kind of radical change that I imagine in the world of statistics and science. Historically speaking, a lot of people have tried to answer that question over many centuries, and I think one of the other claims that I like to make in the book is that none of the conventionally accepted answers to that question are satisfying, or really no conventional definition of probability covers all of the ways that probability is used in practice. So if you study probability, you'll encounter various ideas of it and interpretations of it, but no one of those is really going to be adequate for all of the ways that probability is actually applied in various contexts. So you could say that probability is about counting up the number of ways that something can happen. So, the probability of rolling a 7 with 2 dice is what it is because there are so many ways of doing it and there are so many possible things that could happen. And that's what's basically called the classical interpretation of probability. The problem with that is it assumes that all of the things that can happen are equally likely. And so the definition is circular. Likelihood is probability and probability is likelihood. The interpretation that kind of took over for that historically is what's called the frequentist interpretation. And that is to say that probability is about the long run frequencies with which you would observe something if you gave it many trials to happen or not happen. So a coin flip is 50% because if you flip a coin 10 million times, then about half of the times the coin will come up heads. The problem with that is it doesn't cover events that only occur one time. So, for example, an election in a particular year, a particular country, particular candidates, that election's only going to happen one time. So in what sense is it meaningful to say that a candidate has a 30% chance of winning an election if it can only occur one time? Or if you're talking about things that have already happened, you want to make inferences about causes or events in the past. There is no sense in which those things have a frequency of occurring or not occurring. And the final school of thought that people have used to try to explain what probability is what might be called the subjective interpretation, which is to say that probability is about the degree of belief that we have in a proposition. How likely do you think it is? And the problem with that seems very personal, that you and I might have different numbers that we come up with for the likelihood of events. How can we say that one of us is right if I say, actually I think a coin flip is 75% chance of coming up heads? In what sense am I right? If probability is just personal and subjective and a matter of opinion. So the version of probability that I think ultimately should supplant all of those, and what is this core idea of this writer Jaynes that I mentioned, is that probability is really about logical reasoning in the presence of incomplete information. So what we mean when we talk about probabilities of events or propositions or anything is a number that we assign to it based on the information we have about it, about that event or that proposition. And if we have a certain set of information, then we are forced to assign a certain number to it. So if, for example, we know that a coin is symmetric and we don't know anything else about it, then we are forced to assign the two sides of the coin equal probabilities. And that is really combining the best aspects in a way of the frequentist and of the subjective interpretations of probability. And it's the kind of probability that then can be used for every manner of setting. So inference about scientific theories or predictions about events or forecasting or all these different contexts, they ultimately can fall under the heading of reasoning logically about something that we have only partial information about. And that's what probability should be.
It's really interesting. It sounds like a bit of a paradox because all of us think that we understand what is probability and we use it every day. But in a sense, when you think about it, we don't really know that much, is it?
I think that's absolutely right. I think one of the things that you experience if you start talking to people about probability is that it can make people very upset because on the one hand, it feels very everyday, like something we have a lot of intuition about and we talk all the time about, a chance of rain or a chance of, an event happening, whatever it is. But at the same time, if you really push people, nobody really has a good answer to the question of what do you mean by that? There's a 30% chance of rain tomorrow. And if you don't have a very solid grounding and basically, as I hinted at earlier, if you don't think slowly and methodically about it, you can easily get yourself into paradoxical situations where you might come up with different answers to the same question depending on kind of how it was phrased to you. So people do have a kind of natural upset feeling about probability paradoxes and questions of probability, because I think it touches on this deep kind of insecurity that we have about not really knowing what we mean and not really knowing how to make sense of all this uncertainty that we have about all different things in our daily lives.
So how was the concept of probability developed in the field of statistics?
So statistics, as we kind of think of it now, really wasn't developed until sometime in the 20th century, maybe early 20th century, late 19th century. Probability is much older than that. Probability goes back to at least the 1600s and probably significantly earlier than that, and really has its origins in answering questions about things like gambling games. So basically, what are the fair odds that we should place on a certain bet on a certain outcome in a dice or a card game or something like that. But where it really started to interact with statistics started with the growth of social science. So in sort of mid-19th century, people had been using probability in scientific realms like astronomy to basically make sense of the measurement error that they had in recording their astronomical measurements and extracting from that maybe a best estimate of the position of a planet or the orbit of an asteroid or something like that. And the figure that I identify in the book as I think really kind of creating a bridge between those scientific disciplines and what we call the softer sciences, things like politics and economics and psychology and social science generally, was someone named Adolphe Quetelet, who had a training in astronomy and basically recognized in society some of the same mathematical patterns that he had been trained to deal with in his astronomical career. And so he created what he thought of as social physics, which was the kind of first quantitative social science, and started applying these ideas of probability to studying people. And that really took off, as I said, in the sort of early 20th century or late 19th century. And especially with the theory of evolution and the uses of evolutionary theory in population biology, there was a great demand for quantitative tools to make sense of all of this data that people were gathering in different kinds of biological problems. So that's where the kind of marriage of probability and statistics came from, that statistics is ultimately about just gathering large amounts of information. The word statistics actually comes from a word meaning of the state, and the first applications were problems of data gathering for state interests. But probability entered it when people were trying to do statistical inference and modeling, and particularly in the realms of biology and evolution.
So who were some of the early or mid 20th century statisticians that we perhaps heard of?
Yeah, so the three main people that I reference in the book and that I think are mostly responsible for shaping the field of statistics into what we know today were Francis Galton, Carl Pearson, and Ronald Fisher. And the three of them actually had quite a lot of overlap in their lives. They led similar kinds of lives in some ways, although different in some other ways. But they were all basically Cambridge educated British statisticians, and Pearson in particular is really the first what we would think of as modern mathematical statistician and the first professor of mathematical statistics. But the three of them, over the course of their careers, which spanned from late 19th century to about the 1950s, they created what we think of as the kind of field of statistics, and it was subsequently then refined and developed further. But a lot of the terms and concepts that we use in standard statistical practice to this day, really go back to people like Francis Galton. So if you've heard of correlation or regression to the mean, or linear regression in general, those are ideas of Francis Galton. And Pearson gives us ideas like p-values and significance testing, and the chi-squared test, and many of the kind of standard things that are still part of statistics. And Fisher, I think, has a strong case of being probably the most influential scientist of all time, certainly of the 20th century, because he really made statistics a standard part of science in the way that it's used in millions of scientific papers to this day. And so when you read through a standard statistics textbook, by and large, you are experiencing most of the ideas of Ronald Fisher. So not a name that maybe is such a household name, but I think if you trace back the origins of the most commonly used ideas in statistics and science, they are in many cases the brainchildren of Fisher and Pearson.
So when we think about science, we always like to think that it is quite divorced from the social or economic factors of the day. Was it the case with the statistics, especially from the human aspect or politics point of view?
So the answer is certainly no. But I agree with you that the standard view of statistics is that it is separate from social factors and human aspects. I think when I was studying statistics, I certainly never heard much about the personal politics of any of these people, although I knew the names like Francis Galton and Carl Pearson. Francis Galton's also well known because he's Charles Darwin's first cousin. And so that's presented as just kind of an interesting factoid until you really dig into it. And then you find out that that had an enormous influence on Galton, and that he used his cousin's evolutionary theory in particular to develop what we know as the eugenics movement. And he founded the word eugenics and was responsible for agitating for the agenda of the eugenics movement around that time in the late 19th century. And that was very much a part of his program. And when you read his writing in actual primary sources, you will find that they're inseparable. His statistical ideas are inseparable from the ideas of eugenics and his advocacy for that social agenda. And the same is true for Carl Pearson and Ronald Fisher. So I think the full, complete story of statistics has to include the fact that it is deeply intertwined with the eugenics movement. I wrote an essay for Nautilus magazine called How Eugenics Shaped Statistics, in which I argued that basically statistics is what it is because of its connections to the eugenics movement. So these statistical tools that these authors came up with were in service of that agenda and were answers to questions that could only come up in the course of looking at the kinds of questions that they had, the problems that they were faced with in eugenics and evolution more generally. So, yes, it's surprising, I think, in some ways that how connected these things are. But really, when you go back to the original sources, you'll find that statistics is very much a human enterprise and is very much a product of a particular time and place and a socio-political agenda. And in this case, it was by and large an agenda shaped by the eugenics movement.
So in what ways did, and also nowadays as well, statistics influence the society in positive ways?
Well, statistics is also, going back a little bit further, it is also an enormously important conceptual framework for making sense of observational data and making sense of empirical observations. So, that I think, as I argue in the book, the transformation of science as a result of the growth of statistics is the greatest change in scientific practice, really, since the Enlightenment, since science became what we kind of understand it to be. And there's certainly many things that science has accomplished that it could never have accomplished without statistical reasoning, without those tools to make sense of errors in observation and uncertainty in data gathering. I think that probability, even more fundamental than statistics, perhaps, is an important way of making sense of the world well beyond science. So I think, as we hinted at earlier, when people talk about and think about probabilities, what they are doing is making sense of the incomplete information that we always have whenever we're trying to make decisions in our daily lives. So if you kind of understand probability as the kind of logic of uncertainty or the logic of incomplete information, then I think you would have to recognize it as being as important as, or maybe more important than, deductive logic, that, the kind of ordinary basic tool of logical reasoning that's been around for millennia, that we all kind of recognize as being an important part of good thinking and sound reasoning, actually is somewhat inadequate to our daily lives, because we never really have the certainty of premises and propositions that we need to reason deductively. I never really know for certain if A, then B, and A, and I'm justified in concluding B. What I'm more often given is if A, then probably B, but maybe not B, and I'm given probably A, maybe something that looks like A, maybe some alternative to A. And I have to make sense of this mess and conclude, well, probably B or C or D, et cetera, et cetera. So I think, when it comes down to it, probability is the kind of reasoning that applies to every real life decision, and that people are forced to use all the time in their daily lives. So it's certainly very important that probability exists, and that I think that the tools and the language and the philosophy of probability are a part of the fabric of everyday life. And in especially in times of crisis and uncertainty, like we mentioned with the pandemic, I think people have been confronted with more and more examples of probabilistic reasoning. But what I argue in the book is that statistics, at some point in the course of its development, about 100 years ago, kind of got driven into a bad place. The wrong school of thought kind of won out in these statistics wars of the interpretations of probability and what statistics really was going to mean conceptually. So unfortunately, I don't have a lot of positive things to say about the usages of statistics, in particular in the sciences, except that I think almost despite itself, it has accomplished a great many things. And I think what I would like to argue for in the future of statistics is a version of statistics that's more useful for scientists. I think that, unfortunately, statistics has been mostly a hindrance to scientific progress, or a kind of empty formality that scientists have had to use to get their results published, but that really it's a missed opportunity that statistics could mean so much more than that. And if it were put on a more solid foundation, I think it has the potential to guide scientific progress in some really productive and amazing ways.
So what crisis of modern science do you talk about in your book?
So the crisis that I refer to in the book is what many people will call the replication crisis, or the crisis of reproducibility. And this is something that has emerged over the last decade or so, really starting in about 2011. And that is that there is a large percentage of scientific results, something like 50%, depending on discipline, but hovering around 50% in all different areas of science. So beginning in psychology, but certainly not limited to psychology, economics, social science, biology, neuroscience, you name it. When previously published or established scientific results are attempted to be reproduced, so when people take experiments or original experimental materials and try to do the same experiment again, maybe with more participants, maybe with the same number, they, generally speaking, do not get the same results as the original studies. It's really, I think, a problem or a crisis because it calls into question the validity of those results. So it really, I think at this point, we'd have to imagine that roughly 50% of the kind of settled science that we think of as being established theory is questionable, to say the least. So if it were run again, maybe the effect or the association or whatever the claim of that original scientific statement would no longer hold up. And among the rest, the effect might still be present, but it might not be as substantial as it was originally reported to be. So it's both that previously established results seem basically just to not hold up, and when they do, the magnitude of the effects is also tends to be somewhat milder than originally reported. It might be again on the order of a factor of 2, the overstatement in the effect sizes. And so there are a number of large-scale efforts now to investigate kind of just how deep that issue goes and whether it's present in all these different domains. And as I said, I think that the indications now are that it's not limited to one area of science, that it crosses all different disciplinary boundaries, and that it is an enormously widespread problem. And I think one that calls for some urgent reforms in the practice of science. And the common thread that I argue in the book is that all of these scientific results, they all depend in some way on the use of statistics, and in particular, the practices of statistics that came to the fore in the early 20th century and the work of people like Ronald Fisher. So when we talk about things like null hypothesis significance testing really being the main one, or p-values, I don't know if people have heard of that. Those are really the common language of statistical inference as it's used in the sciences, and all of these results that are failing to replicate have in common the fact that they use that language and those tools, and it's not a coincidence in my mind.
So is it a case that the statistical tools developed in the beginning of 20th century are not really suited to the structure of data, for example, and amount of data that we have nowadays? Or is there something else?
Well, I would argue that they were never suited to any of the problems that they were used for, even really going back to the early days. But I think certainly the growth of data gathering has exacerbated things. So what is really missing, as I argue, in the uses of these statistical tools is any acknowledgement of the prior understanding that we might have about an effect or a scientific theory or an experimental hypothesis before the experiment is run. And there are a large number of domains where we do have strong prior information, and we should have reason to think that a scientific theory is unlikely before we even start gathering data on it. So like one of the examples that I point to in the book, and it's not an atypical example by any stretch, but just one of the ones that's sort of easy to describe and understand, is a study about looking at a picture of the statue, the thinker, and then being asked how you feel about belief in God and religion. And the claim in this scientific study that was run on about 50 participants or so was that looking at a picture of this statue for 15 seconds made people approximately 30% less religious, or it lowered their belief in God on average by about 30%, which, if you try to fold that into our understanding of the world, you should, reasonably speaking, be pretty skeptical about, I think, ahead of time. So without having seen the results of the study, you'd probably assign that theory a very low probability of being true. And then the study showed some results that are maybe unlikely to have occurred if that theory was not true, but were they unlikely enough to shake us of our skepticism? And that's really the balance that needs to be used in statistical inference, and the weighing of probabilities between our prior understanding of the world and our guess about how likely something is versus how likely or unlikely the data would be if that theory were not true. And essentially the template of statistical inference just doesn't allow for that kind of prior skepticism. It doesn't allow us to inject our prior understanding because it's viewed as subjective and corrupting of the scientific method. But I think what I would argue in the book is that it's an essential part of making sense of all this experimental data, especially now that we have the possibility of just generating so much data and testing so many different types of hypotheses and theories simultaneously. We're going to find some results that seem statistically significant just by accident. And if we don't have a way of expressing prior skepticism about the validity of those ideas, then we're just going to be chasing after these statistical artifacts, essentially. And that's what I think is going on with the crisis of replication.
So in which ways would you try and sort of resolve it, or what kind of revolutions do we need in the statistics?
Right. So what's needed is an allowance for prior information, as I mentioned. So the alternative school of thought, sort of the minority school of statistics that has been around for quite a while, but was marginalized, especially during the mid-20th century, is Bayesian statistics, which is essentially a different framework of updating probability assignments based on information. So it includes, for example, what's called the prior probability, meaning the probability that we assign to a hypothesis before allowing for or conditioning on experimental data. And that is what can be used to set the bar higher for theories that we should discount as being very unlikely. And it's a way that we can express skepticism about scientific claims before we start analyzing the data. So that, as I said, is a school of statistical inference that has been marginalized, mostly because of accusations of it being subjective and personal. So I think the revolution that I'm talking about is not just about mechanical methods and different techniques. It's really about a different way of thinking about scientific inference more generally. And as I would describe it, recognizing the fact that all inference is subjective and up to kind of consensus opinion and judgment, and that science is ultimately a human enterprise. It's not number crunching and not purely mechanical. So in a sense, subjectivity is what's needed. And I think a recognition of the fact that we can't do science and statistics without a subjective element would represent quite a large shift in scientific philosophy. That I think that these statistical authors of the 20th century, particularly in the service of their very controversial agendas, they wanted statistics to be mechanical and objective and impersonal. And I think in some ways that was a false promise that we never should have accepted, and that we are now kind of paying the price of that when we are unable in our analysis of these kind of scientific theories to express our skepticism about them ahead of time. We just don't have a language for that because it's not a part of the statistical program for various reasons that were by design.
This is so interesting. It's like an injection of healthy biases, because as we know, the scientists try to eliminate as much bias as possible.
Yes, I think that's right. I think another way that I could describe this whole program is almost a defensive bias. And I think that it's even a statistical term in a funny way, that there are various kind of value judgments that are embedded in the language of statistics. So one of them is something called an unbiased estimator, which is a purely kind of mathematical statistical property, but it seems to carry with it a kind of goodness that you of course would not want to be biased. But really, depending on the situation, these unbiased approaches can lead you into some very dangerous and bad consequences. And I think what I would argue for is that, first of all, bias is impossible to avoid because what bias represents is our prior understanding of the world. And we always make decisions of every nature, including scientific inferential decisions, in the context of what we know about the world and the ways that knowledge is situated in particular contexts. So bias is inevitable, but it's also desirable. That bias is what allows us to discount claims like that looking at a statue for 15 seconds will make you less religious, or even sort of more pseudoscientific claims about paranormal psychology or or conspiracy theories or whatever it is, there's always going to be some experimental evidence that you could see as being in support of those claims if you interpret it the right way. But bias is what allows us to come together as a community and decide this explanation is the one that we lean towards, and this explanation is the one that we discount. And this is what we consider scientific truth, and this is what we consider false. So yes, I think bias has gotten a bad rap, and I would like more bias in the practice of science and statistics, even as dangerous and unappealing as that sounds.
And now thinking about the bigger picture, what will be the key implications of statistical literacy in our society, but also exploring the statistical field as well to find new ways?
So I think, as I've indicated, statistics is a part of our everyday lives, and it shapes decision-making at every level. So I think we all have a stake in these kinds of statistical and scientific truths, whether that's at the level of public policy about environments or healthcare or economics or whatever, or whether it's even just at the personal level of, what decisions are we going to make about our personal health. And probability is also a part of our daily lives. So, in the book, I give many examples of probabilistic reasoning as it has affected people's lives in different settings. So, particularly in medical decision making about, test accuracy and the percent chance that we might have, say, a disease or a medical condition based on the results of a test. I think that's a kind of probabilistic decision making that people are generally not very well equipped to handle, but could be with just a little bit of kind of thinking through some simple examples. There are also examples of probability in the law and in settings like legal verdicts of court cases that arguments have been presented in trials about the facts of a case being very unlikely, and therefore being very unlikely that an accused person is innocent of a crime. And people have been wrongfully convicted. I tell this story in the book of Sally Clark, who was wrongfully convicted of murdering her two children because there was evidence presented at her trial that the odds were very small that if she was not a murderer, that she would have these two children die under the circumstances they did. And that argument was criticized by experts, but it wasn't really understandable to the jury. And I think that had people had a little bit more probabilistic literacy, they maybe would have been able to make sense of the different ingredients of that inference that they would have had to include, for example, the prior probability that she was guilty of this crime, that it was an extremely unlikely event that she was being accused of. And so they were really being asked to weigh two unlikely propositions and decide which one was the more unlikely. So I think that's, at the end of the day, the kinds of decision making that people will be able to do if they have more training in statistics and probability. But unfortunately, if they study statistics, they are by and large, educated in the ways of statistics that fall into these logical fallacies. And so right now, people who are statistically literate are generally not much better equipped to use probabilistic thinking, because the standard training in probability and statistics is kind of unfortunately muddled and confused in the ways that that the fundamentals are described and the foundations of it. So I think, statistics needs to repair its own foundations, and then it can worry about educating the rest of the world.
Sounds like it's a good time to be a statistics rebel.
I certainly hope so. I like to think of myself that way, and I think that there are many others out there who are interested in joining the cause. But first, we need to join up and get our message straight and organize ourselves.
So what discoveries along your journey to writing your book, Bernoulli's Fallacy, surprised you the most?
So one of the things that surprised me is just how vibrant this debate is and continues to be. You know, I knew that there had been very active and heated debate about the nature of probability for centuries. But I don't think I understood before I really started writing the book just how ongoing that debate is and how many people are out there struggling with statistics and probability concepts and really feeling a need for some clarification of what these things mean. I heard from a professor of mine actually at Berkeley who is in the Department of Statistics and has been teaching statistics for many years. And when I described the book to him, he said he actually avoids teaching statistical inference because the concepts never made sense to him. And this is a tenured professor in the Department of Statistics. So I think it's surprising to me that no one really seems to have a complete answer to this puzzle. And that many people have felt for years since learning about statistics that something didn't quite add up, and they've never really felt comfortable using statistical ideas, even people who use them all the time in their research work and in their scientific work. So I think it's been great to learn about those stories and to connect with people who feel a real need for a treatment like this to help iron things out and give them a solid foundation to then do their work.
And when we are allowed to go back to cocktail parties, for example, and dinner parties, do you have any favorite statistical or mathematical factoids that you have in your pocket to stun your company with?
Yeah, so first of all, I think the suggestion of going back to a cocktail party is somewhat comical. I have, as it happens, 3 small children under the age of 4, so I don't imagine I'll be returning to any cocktail parties even when the pandemic is done anytime soon. But I think some of the things that I've learned about in the course of writing the book have been quite interesting and kind of surprising little nuggets of information. So, you know, one of the things that surprised me about Bernoulli's work, going back to around the year 1700 and the foundational work by Jacob Bernoulli in the field of probability, is that he ends his book Ars Conjectandi with an example of random sampling, and he's showing an application of his method to deciding how big a sample size would be necessary to do a kind of inference about, say, the mix of pebbles in a large urn. Okay, so maybe there are black and white pebbles, and he needs to know with some certainty within some margin what that mix is. And he comes up with the sample size 25,500. And then the book abruptly ends. And there was a theory, Stephen Stigler in his History of Statistics book, I think expressed the theory that basically Bernoulli saw that figure and gave up because that was a sample size that was so large that he could never imagine performing an experiment of that size. It was larger than the population of Basel, Switzerland, where he lived at the time. And so it was dispiriting to him that you could even talk about such numbers. But then flash forward a few hundred years, and there was a famous psychological or sociological theory about what's called the 6 degrees of separation that originally involved a sample of a few hundred people trying to get letters to a particular person in Boston, Massachusetts. And it was, on average, it took about 6 links in the chain from these randomly chosen people elsewhere in the country. And that theory was updated in 2007 to 7 degrees of separation. And the data that it was based on in the updated study was a collection of 30 billion text messages and the conversations that people were having over the period of a month. And so I think it's just a testament to how much has changed in the lifetime of these ideas, that in a few hundred years, we've gone from a sample size of 20,000 seeming so improbable and dispiriting in how large it was, to a fairly reasonable scientific study using a data set of 30 billion samples. And I think that, it's also an amazing testament to the permanence of these ideas, that they continue to be relevant, at all scales, from small samples to extremely large samples, that we're still using those tools and techniques.
Well, this has been truly illuminating discussion. So can you tell us, what are you currently working on and what will be your next project?
So currently I'm working on spreading the gospel of Bayesian statistics. I am teaching and intend to keep teaching courses in the logic and the philosophy of probability, including some amount of the history of probability and statistics. I'd like to give people more resources who are looking for a kind of complete treatment of that version of probability. So really connecting back to the logical foundations of it, and giving some guidance about what I think can replace statistics when we're done demolishing statistics as it currently exists. And beyond that, I'm also continuing to write about statistical and probabilistic reasoning in day-to-day lives, and the pandemic continues to, unfortunately, provide lots of examples of relevant contexts for using probability and statistics. Beyond that, I would like to, I think, return to my roots somewhat and think about and write about the ways that these subjective and social factors have influenced even fields like pure mathematics. Because I think that statistics, in many ways, it's unsurprising that it has a social dimension, even though people have tried to deny that for many years, that it really is a very applied discipline, and it connects to areas of life that people have strong political opinions about. I would like to argue that that same dynamic is present in essentially every area of human thought, including pure math and the ways in which we decide what statements are mathematically true and what propositions have been proved, I think is something that is subject to much more social consensus and political factors than people are usually ready to acknowledge. And so that's something that I'd very much like to explore, and I think is a message that people might be prepared to hear.
And what would be the best way for our listeners to find more information about your work and also your book?
So listeners can go to my website, aubreyclayton.com, and find all kinds of information about my writing and teaching. They can also find the book Bernoulli's Fallacy through all different booksellers, including Amazon and bookshop.org, and through the Columbia University Press website.
Well, thank you so much for joining me today.
Thank you. It's been a pleasure.